So today we are going to start stereoisomers. So we have already seen the geometrical isomer. Now we are going to look about stereoisomers. This is actually stereoisomers. So what is actually stereoisomers? Are the molecular conditions for the stereoisomer? The molecular formula must be same. The molecular formula must be same and structural formula or connectivity same. Structural formula and connectivity should also be same. That was the not necessary condition for the geometrical isomer or not geometrical, the structural isomer. The condition was not same for the structural isomer. Different location of atom in space. So the location of atom in space must be different. Like we have a molecule A, B, C, and D. All the four are connecting like this. One is connecting like A, then B, then C, then D. Okay, one connection is like this, and one connection A is below, B is above, C is below, and D is above. How it is like that, we're gonna see in our examples. So we're gonna see in examples how does it make sense and all. So now continue with if we talk about, let's say, like we have H, here we have C double bond C H, then Cl, then CH3, then CH3, then C double bond C H, then Cl, then H. So the Cl and H are together here, and Cl and CH3 are together here. So these are actually different molecules. These are actually different molecule. Connectivity is same, but the arrangement in 3D is different. So that are called the stereoisomers. So we have to look at into deep how many types of stereoisomers are there and all. Right. So if I look to the more examples, like the carbon is here, H is there, then Cl is here, Br here, then another carbon tetrahedrally attached to another C, Br, then C, then H, then Cl, then Br, then Br, then H, then Cl. So these together are stereoisomers. These together are stereoisomers. Okay. Now, how many categorization of stereoisomers are there? A stereoisomer is further categorized. Stereoisomers are further categorized into conformers, geometrical isomer, and optical isomers. You can say that first it is conformers, second it is geometrical isomers, and third it is optical isomer. Conformers, geometrical isomers, and optical isomer. That's how they are connected. Now, first of all, we're going to talk about geometrical isomers. Geometrical isomers. So, geometrical isomers are what are the geometrical isomers? Let's say we have a compound C double bond C H. Here we have H. Here we have CH3, and here we have CH3. So if you look into the deep, how this compound is formed, right? So this compound is formed with two p pi orbitals are overlapped with each other. That's how. Then we have looked into depth in the chemical bonding. Then here we have H, here we have CH3. Here we have H, and here we have CH3. Now let's say we have two H bond. Now can it be rotated? If we have two p orbitals overlapped perpendicular, can it be rotated? No. If they are stick like this, you can't rotate it like this. So this compound is different from, this is A, and this is different from the compound where we have CH3 here, H here, and CH3 here, and H here. So A and B are different. That's how they are called geometrical isomer, because they are different. They have different position relative to the restricted rotation. What is the restricted rotation? This is That's how two p orbitals are overlapping laterally. So this is a restricted rotation. You can't rotate two objects which are stick like this. You can't rotate it like this. So one compound is going here. Four compounds are there. Now you can't rotate it. Remember, you can't rotate that CH3 and H. So when we have a rotated compound we got, so that is a different compound, right? So what is the relation between both of them? Both are known as geometrical isomer. So we know A and B are different. And A and B together are isomers. And A and B together are stereoisomers. And A and B are geometrical isomers because they have different position through restricted rotation. They have different position through restricted rotation. Now, how many ways we could define the geometrical isomer? First, it is our double bonded system. Geometrical isomer itself is a very deep topic. We're gonna look substituted cycloalkanes. C, it is cycloalkanes. D, it is resonating structure leading to geometrical isomer. E, it is triphenyl system. F, it is bicyclo compounds. G, it is miscellaneous. So these all are the category of geometrical isomer. So first of all, we have double bonded system. We have initially double bonded system. All right, double bonded system. Now in double bonded system, it is the very common type of geometrical isomer which is known as double bonded system. In double bonded system, let's say we have C and carbon are attached, C and D, and A and B together we have, right? Now, what is the condition of this double bond to show geometrical isomer? Does all these double bonds show geometrical isomer? No, all the double bonds show geometrical isomer. So, which show geometrical isomer? If A is not equals to B and C is not equals to D. The condition should be A should not be equals to this A, should not equals to this B, and this C should not equals to this D. That should be the condition of geometrical isomer, right? Now, we have an example for this. We have C double bond N. There is a lone pair H, and H then CH3. Then now, could it show GI? Yes. This could also show GI because it necessarily not need to be carbon. It could be oxygen. It could be nitrogen. We're gonna look some advanced problems where we're gonna see geometrical isomer doesn't happen only in case of carbon. It might be oxygen. It might be nitrogen and some more other elements, right? So yes, these two are different. Hydrogen and CH3. The lone pair and H are different. So this will show GI. This will show geometrical isomer, and we have nitrogen lone pair hydrogen, double bond nitrogen lone pair hydrogen. This will also show GI because this nitrogen lone pair and hydrogen. This will also show GI. I mean, this is the GI of the first compound. Also show GI means these together are geometrical isomers of each other because they cannot be inverted back to its original one. Right, this cannot be converted into this, and this also cannot be converted into this because these both are totally non-convertible structure because of the restricted rotation, right? Now there are some compounds like we are doing some very good question, which of the following will show geometrical isomer? Which of the following will show geometrical isomer? First, we have C double bond C, CH3 and Cl, and H and Cl. Will it show geometrical isomer? Tell me, will it show? Only the condition we need to check that these two are different and these two are different. That's all. So yes, it will show geometrical isomer. Second, CH3 or C double bond C, H and Cl and CH3. Will it show GI? No, these two are same, so it will not show geometrical isomer. Third, we are talking about. Third, we have a H, C, Cl double bond. Here we have so it will show geometrical isomer because the carbon is different in these two. In these two positions, the carbon is different, and these two positions, the carbon is different. Fourth, show the geometrical isomer. Let's see what is the fourth question we have. The fourth question we have is the oxygen and double bond C and H and Cl. So these two are different, and the two positions are different. These two are different, and these two are different. So it will not show. It will show geometrical isomer when the cycle is connected like this. So how we check that both of the two valencies are different? First we'll check 1 and 1 dash. Yeah, these two are same. Then we'll check 2 and 2 dash. These two are different. When these two are different, we're gonna see that it is a different compound attached through a two different valencies of carbon. And fourth we have, and fifth we have like H C H double bond C H and Br. Will it show geometrical isomer? These two hydrogen are same, so it will not show geometrical isomer. Now we're gonna look at sixth question. We have this compound we have, and this compound we have. So here these two carbon. If you look at these two carbon are different and these two carbon are different, so it will show geometrical isomer. I hope you are going to understand that the two carbon we have, they are attached to this double bond. We have to check these four compound attached to it, and these two must be different, these two must be different. Maybe these two A and C and B and D could be same, but A, B and C, D must be different. When they are attached to a cyclic compound, we have to check each and every side. That's 1 and 1 dash, 2 and 2 dash. So here we are counting as 1 dash, 2 dash. Here we are counting as 1 and 2. So when 1 dash are different, 1, 2, 1 dash, 2 dash. So here also 1 dash and 1 are different. So that's how we check. We have seen a lot of times in the how we name, how we number the carbon in nomenclature. And if we haven't seen there, then we're gonna look at here. Okay, it is not a big deal. So this is our seventh question. In seventh question, we have hydrogen, carbon, chlorine, double bond C, and this. Will it show geometrical isomer? No, it will not show, because 1, 2 and 1 dash and 2 dash, they both are same. When they both are same, it will not show geometrical isomer, because A and B are similar, or we can say C and D are similar, so it will not show geometrical isomer. If we look at the eighth problem, we have HCl double bond. This type of compound we have, and so it will also not show. 1 and 1 dash are same, and 2 and 2 dash and 2 are same, so it will not show geometrical isomer, because both the valencies are different. Okay, if we look at the ninth problem, we have this is, we have compound double bond C, H and Cl. Now 1 and 1 dash are different, so it will show geometrical isomer. 10th problem, if we look at, we have a compound like this. So yes, it will show GI, because these two carbon, this carbon A and B, both have the different valencies. Okay, both the valencies are different of these two carbons. 10th we have. 11th, in 11th we have oxygen, right, like this, and double bond C and CH3 and H. So 1 1 dash, 2 2 dash, 3 and 3 dash, all the same. So this carbon has both the valencies similar. So when both the valencies are similar, it will not show GI. It will not show geometrical isomer. Now we have a very important type of example. We call it as an alene system, right? Alene system. 12 examples. 12 example 1, we are going to see. We have carbon double bond, carbon double bond, carbon double bond, carbon. Here we have hydrogen and chlorine. Here we have hydrogen and chlorine, right? So now will it show GI or not? So let's say we have here, and let's say we have, look at this carbon, we have p orbital and p orbital over the plane of the surface. Okay, right, these are making bond. Now we have another p orbital which is having perpendicular to it. Okay, because px, py, pz, all these take participate. So if we talk it as a px, okay, if we talk it as a py, and py are making bond, pz and pz are making bond, and px must be in the hybridization of sp. It says sp hybridization, so s and px, a little bit chemical bonding involving here in organic topic, right? So f py, py, pz. Now which again it has py and py orbitals. I'm not going to go deep in the chemical bonding because it is not the chemical bonding topic. It is actually organic topic. So I'll refer you to learn the chemical bonding first. You need to know the chemical bonding before learning the organic chemistry. A little bit chemical bonding you should be knowing. Hybridization, what is it? Okay. So now here it is involving of py. Now whenever again a bonding is forming, so it should be in the plane because it is sp2 hybridized. It is also sp2 hybridized. Okay, right. So when bond is forming like this, so the one bond should be inside the plane, one should be above the plane. Okay, one should be inside the plane, and one should be above the plane. So yeah, one hydrogen and chlorine are like this. They are in the same plane. So if you rotate one, like if you rotate one, so relative distance gonna change. Relative distance gonna change, right? If something is in this plane and we rotate one like this, so the relative distance of my thumb to another thumb is going to change. But when they are perpendicular to each other, if I rotate my one hand, so the relative distance between thumb and thumb not gonna change because it was same here, now it is same here. So in this case, eventually we are getting that all these the four atoms, or we can say six atoms, are in the same plane. So yes, it will show Gi because the relative distance gonna change. Now look, very good example of 13. We have CH3 double bond C, double bond C, H and Cl. So look deep into this example. So how this example is, we have let's say px and pz, let's say py and py are making bond, and we have pz and pz are making bond, right? Now one bond is in the plane hydrogen and chlorine, and one is hydrogen and cs3 below and above the plane. One is like this and one is like this, right? Now if I rotate the one, the distance and this distance is same. You must remember then when we are reverting, when we are twisting it about the restricted rotation, the relative distance gonna change. When relative distance not going to change, then it is an identical compound, right? So it is, when we change this H2CH3, then the compound will remain identical. Okay, so it will not show Gi because on the changing the it through the restricted rotation, the relative distance is not going to change. The compound is similar, right? So what is the key point? Key point is when in alene system, we call it as an alene system. In alene system, when we have odd number of bond, it will show Gi, and we have an even number of bond, it won't show Gi. Condition must be satisfied. Condition must be satisfied. What is the condition? That A should not be equals to B and C should not be equals to D. That condition has to be satisfied. Here we have even number of bond, 2 number of double bond. Here we have 3 number of double bond. So it is showing Gi. It is not showing Gi. So simple it is this. Okay. Now let's say 15th illustration. We have deuterium, carbon, hydrogen, double bond, carbon, and oxygen. Will it show Gi? No. Even it is satisfying the condition, but we have even number of double bond, 2 double bond. Both are going to be in a perpendicular plane. So on changing the 180 degree to the other molecule, on rotating 180 degree to the restricted rotation, the relative distance is not going to change. So when the relative distance is not going to change, it is still not showing GI. If we talk about the example 16, we are in my lectures. It is uh, very my what is the my point that in my lectures you will find lots of examples, lots of example. You don't need to go beyond my cover, means beyond my syllabus, or you can say beyond my lecture, to do the more numericals or numericals in case of physical chemistry, and in case of organic chemistry you don't need to go beyond that. That is very enough. Okay, so it is also even number of double bond, even the condition is not satisfying in 16, so it will not show GI. When we are talking about this 17th question, hydrogen, chlorine, carbon, chlorine, double bond, C, double bond, C, double bond, and now we have 3, 1, 2, 3 number of double bond, so it is similar to the single bond. Okay, 3 number of double bond, it is similar to the single bond. They must be continuous. Continuous is also called the alene, and it is also satisfying the condition, so it will show GI. 18th I have HC and CH3. Double bond C, double bond C, double bond C. So it will also show GI. 19. HCCl. Double bond C, double bond C, double bond C, double bond C. H and Cl. We have even number of double bond, it will not show GI. 20th. Oxygen, hydrogen, double bond C, double bond C, oxygen and hydrogen. This is a positively charged oxygen, so it will also not show GI. GI will not show because we have even number of double bond, right? Now it is not necessary to be the double bond only. If we have the ring also, this type of ring also we have. So this ring can also be convert into like this. Only in case of calculating the GI. Remember, not it is not equivalent. These two are equivalent while observing whether show geometrical isomer or not. That these both are converted. Okay, 21. So this is equivalent structure. These two are equivalent. How it is equivalent? Again, it is related to chemical bonding. The pure metal we have here, we have pure metal, and you will apply your chemical bonding concept here, and you will get why it is so. Okay, now we have a lot of compound like cis trans. Okay, so we're gonna see that the geometrical isomer is further categorized cis trans, EZ system, and syn anti system. Okay, right, that we're gonna look in our next video.